So first I have to simplify, or I should say factor first the denominator, into x minus 1 and x minus 2. I have to get my table going with f prime, f of x in the middle. If you have any questions anytime, please stop me. It's very important. Your progress in my class, I hope you know, it's very important to me. Okay, so obviously this function is not defined at 1 and 2. No question about it. Undefined at 1 and 2. Now I can simplify and finally get x over x minus 1. I need to determine limits. So I have to write that x equals 2 is a whole. I have to write that x equals 1 is a vertical asymptote. Why? This stays as a factor, so this must be a vertical asymptote, but this went away, which means x equals 2 is a whole. I have to plug in 0. When I plug in 0, I get 0. I have to determine this limit, this, and this, and then I can move on to the first derivative, not before. So I start with the limit at negative infinity. So limit as x approaches negative infinity from x over x minus 1, I meant to write. That clearly is 1, because when you use L'Hopital's rule for infinity over infinity, you will get 1. So it's infinity over infinity. When you differentiate the top, you get 1. You know, differentiate the denominator, you get 1. Then the answer is 1. Of course, you did not make use of infinity or negative infinity, so there is no difference. It's a horizontal asymptote at both ends. Now, when I determine this, I know it's a whole. All I have to do is plug it in. 2 over 2 minus 1. 2 over 1 is 2. So the open point or the hole in the graph will be 2, 2. Finally, I need these two with 0.9 and 1.1. So I determine the limit as x approaches 1 from the left of x over x minus 1, and then limit as x approaches 1 from the right from x over x minus 1. So when I plug in 0.9, of course, this is a positive number, but this is 0. That's the problem. That's why the answer will be negative or positive infinity. So when I plug in from the left, which is 0.9, the denominator on the first one is negative. So that's why this is negative, so that this is negative infinity. When I plug in 1.1 from the right, this becomes positive, and that's why the answer here is positive infinity. Yes, no?
Did you have to write out like the limit stuff?
No, I'm fine. If you put it in the table, I assume you know how to determine that, and I'm fine. If you don't write this, it's fine. But I'm writing it for students who did not write anything. So just to make sure that they understand where it's coming from. Is that okay, everyone? Yes? Okay. Now this is completely done. There is nothing else we can find about the function from the function itself. X and y intercepts, asymptotes, holes in the graph, that's it. Nothing else. Only now I move on to the first derivative and I differentiate this function. So when we differentiate x over x minus 1, so f prime, the top function prime is 1 times the denominator plus, minus x, in parentheses, I differentiate the denominator and I get 1 over x minus 1 squared. So then, x minus 1 minus x over x minus 1 squared gives us negative 1 over x minus 1 squared. This can never be 0 and is always a number less than 0. All this is always negative, which means the function is decreasing at all times. Why is it not possible to be 0? Is because a fraction is 0 only when the top is 0. But this 1, poor 1, can never be 0. So then I go back to the table. I write negative and negative all the way. But now this is the moment of truth. If these two And I worked with Eddie on a problem and I did pay attention on something and I said, oops, it's not working. So the function, I was expecting the function to decrease and it was increasing. So I knew something was wrong. So we went back to the drawing board and we found the error. Okay, so from 1 to 0 and to negative infinity, that's okay. From infinity to 2 and then to 1, it's okay. So it appears that everything works well. Now finally, I have to determine the second derivative. And the second derivative will be determined on this, but written like this. Because when I find the second derivative, I bring down negative 2. I get 2, x minus 1 to negative 3, and the answer is this. I need to study the sign. This is can be positive or negative, but definitely can never be 0. There are no inflection points. But when I study the sign of this function, I look at it like this. Because it's easier. You need to do this? No. Plug in an entire function if you want. But I prefer to simplify it when it comes to, because this is always positive, I don't want to worry about it at all. So the sign of the second derivative is given only by this quantity. So before 1 is negative. After 1 is positive. So after I show all this, of course the function is not symmetric and I have to write that. It's part of the problem. F of negative x does not equal f of x, does not equal negative f of x. It's not possible for a function, so not symmetric. It's not possible for a function with a hole at 2, 2 and a vertical asymptote at 1 to be symmetric with respect to the y-axis or with respect to the origin. So that's why I cut it short and I wrote this. So someone who grades this understands that I know what I'm talking about. It's not symmetric and I didn't really have to go through all the steps. So then the graph, when we graph functions with asymptotes, we have to start by graphing the asymptotes. That's our first step. And this function has a whole and 2 asymptotes. It has y equals 1. It has x equals 1. And it has 2, 2, an open point. So it crosses at the origin. So the function is decreasing from 1, crossing at the origin, and going to negative infinity. From 1, crossing at the origin, going to negative infinity. On the other side, it's coming from positive infinity, going through this hole, and approaching 1. And this is the graph of the original function x minus 2 over x squared minus 3x plus 2. So please practice this because this is our one of the 3 main applications of this chapter, and you will be given something like this to graph. Is it clear? It's okay, so yes?
Oh no, I was just like,
Jake? Okay, thank you. So this is the power of calculus, being able to put together the information from the first and the second derivative and being able to graph this with no calculator. Yes, you can check, but there is no need really. So you have everything. There is no secret here. You have everything. You know everything about this function. Okay. So back to 4.4, L'Hopital's rule. We've been using it for a month, but it's actually presented in chapter 4. But we didn't want to wait. It's so important to understand it and be able to use it. 7 indeterminate cases. Most of them, I would say, are okay. 3 of them are not as friendly. So, number 1, ratios. And we have 2. They're nice and friendly. L'Hopital's rule is applicable here. Not a big deal. We have one difference. Number 2, difference. So let me just reemphasize. What does indeterminate case mean? It means no one knows what to expect. That's what it means. That infinity over infinity can end up being -3. That 0 over 0 can be 1/5. The difference infinity minus infinity could be 2. So when we talk about indeterminate cases, we say, I have no idea what to expect. Anything is possible. That's the indeterminate case. Okay. 3, product. 0 times infinity. And you can say, really? Yes. 0 times infinity could be 1500, or it could be 0, or it could be -3. Anything. And the last are powers. These are not friendly. And there are 3. 0 raised to 0, 1 raised to infinity. And you can say, really? Yes, really. It can be anything. And the other one is infinity raised to 0. These last 3 are the most involving. The difference is really not applicable a lot here with L'Hopital's rule. The ratios we saw, we refreshed our memory last time. So what I would like to do today is product and the powers. Okay, so let's choose from products. If you have your book, feel free to choose. We are on page 308. And I'm going to choose a couple of powers. And here's one, number 42. And we have limit as x approaches infinity from the square root of x times e to -x divided by 2. This is not a ratio. This is not a power per se, and this is not a difference. So let's see what it is. Now you understand how important it is to plug in and see what type of case it is. It could be any of those 7 cases, or it could just be 5, and you're done. So we have to plug it in. So please tell me, where does this go when x approaches infinity?
Infinity.
Yes, excellent. Where does, piece by piece, where does this go when x approaches infinity?
Infinity.
Very good. Where does this go? Negative infinity. And now finally, where does this go?
0.
Right. So we uncovered a 0 times infinity situation. This is not an enemy, really. A very simple algebraic manipulation, very simple, will change this into a ratio. And that's what we want. We want ratios. How come? Exactly. We want to change everything into ratios. That's our target. We want these. Okay, perfect. So then, can anyone give us a very simple algebraic manipulation that will change this into a ratio?
Infinity over infinity.
Correct. What should I do to this product to change it into a ratio?
Change the 0 into 1 over infinity.
Nope.
No.
So I probably didn't express myself correctly. The function is the square root of x times e to -x over 2. I want the function to be changed into a ratio.
Bring the e down.
Right. First of all, it doesn't even belong there. It has a negative power. Why would it be there? It shouldn't. So, excellent, hon. Thank you. Good. Now let's try again. The top goes to?
Infinity.
Perfect. The bottom goes to? Awesome, isn't it? So then, limit as x approaches infinity. We can apply L'Hopital's rule. The top differentiated will be?
1/2 squared of x.
Excellent. And the denominator differentiated will be?
E to the x over 2
Times?
1/2.
Excellent. Do we understand this step before we continue simplifying? Is this clear? Yes? Everyone? Okay. So now I have limit as x approaches infinity, 1/2 the square root of x times e to x over 2 times 1/2. Where does this go?
Infinity.
Perfect. Where does this go?
Infinity.
And where does this go?
To 0.
Excellent. Therefore, y equals 0. Horizontal asymptote at infinity. So what have we learned here? Is that in the case of a product which is 0 times infinity, we were able to, by simply manipulating the function, we were able to change it into a ratio.
Is that 1/2 outside the radical?
So this is 1/, and I only, yeah, if you want, you can flip this and write 2/, but I kept it in the denominator. I only brought the numerator to the denominator.
Okay.
So let me show this in a different way. Maybe that's clearer. So it's 1/2 the square root of x, everything divided by e to x over 2 over 2. I copied the numerator, the fraction from the numerator, and I flipped the denominator. And then I simplify. Is this better?
Yeah.
Is this better? Sorry, my apologies. I should have done that. So that's how we get this. 1/the square root of x, e to x over 2. That's why these two approach infinity, and 1/infinity approaches 0. Is that better?
Mm-hmm.
Perfect. Other questions from me here? Is this okay? Okay, so let's look at 46. So as I said, limits that turn out to be products, indeterminate products, I meant to say. Most of the time, I shouldn't even say that, but some of them are friendly. Let's put it this way. I don't want to generalize. Okay. So where does x go? Good. Where does 1/x go?
0.
0, right? When x approaches infinity, 1/x approaches 0. Is that okay? Where does this go? Yes. Again, infinity times 0. A simple algebraic manipulation on the function, just the function, look only at the function, x times tangent 1/x, will clear the problem easily. So what do you think we should do? Now, let me just give you a hint. On the previous problem, what if I keep this in the numerator and I bring this to the denominator? That'll be a total catastrophe. Here's why. Because then the denominator will have x to negative 1/2. And this situation is not, maybe I shouldn't say catastrophe, it shouldn't be that big of a deal. But if I have something more complicated, the square root of x squared minus 4x, I will always have a ratio to deal with in the denominator, and I will never get rid of it. So the best thing and the easiest thing to do was to bring this one, which already had a negative power, to the denominator. Now here, how do I think here?
Do we want to make that into a ratio?
Yes, I don't want to touch the tangent. Because if I touch the tangent, I bring it to the denominator, it will have a -1 as a power, and I will never get rid of it. So I want to work on this tiny, tiny little x. What do I write? Exactly. Because when I divide tangent by 1/x, I have to flip 1/x. And now let's see what we have this time. The numerator goes to
0,
perfect. The denominator goes to
0.
yay. That's what I wanted. Either one. It didn't matter to me if it was infinity over infinity or 0 over 0. Couldn't care less. Both of them are friendly. Very friendly. So then, the numerator differentiated will be
Secant squared of 1/x times -1/x squared.
excellent. It's such a leap forward to remember that 1/x prime is -1/x squared. You'll see why very soon in chapter 5. And the denominator prime is, luckily for us,
-1/x.
right. And here's what happens. 1, 1. And now, where does 1/x go? We have to start with the inside of the function. 1/x, when x approaches infinity, 1/x goes to 0. And now we're talking about secant 0 or cosine 0. 1. Therefore, y equals 1 is a horizontal asymptote at infinity for this function.
Secant squared goes to 1.
Yes. Remember, secant is 1/cosine.
Okay.
That's why I'm not even asking you to think in terms of anything else but sine cosine. Since secant is 1/cosine and cosine goes to 1 when x approaches 0, then so is
So it's 1/1.
it's 1/1. Correct. Okay. Is this clear? Okay. Would you like to move on to the last one? The powers, the unfriendly ones?
Yes.
And then we'll come back and do more problems, of course. Okay, we're talking about powers now. With powers, you're going to see a lot of steps. Does anyone remember, and I hope you all do, how do we differentiate a function raised to another function? Thank you. Keep that in mind. Did you hear what Greg said? He said log. Okay, good. So let's take a look at, let's start with, doesn't matter, let's say 56. Limit, as x approaches 0 from the right, from tangent to x, everything raised to x. Okay. We start from the inside. Where does this go?
0,
Excellent. Where does this go?
0,
Where does this go? Oddly. It's 0 over 0. 0 raised to 0. So then, of course, I have to take the function aside, write it as tangent to x, everything to x, and then, again, what do you think we're going to have to do to both sides? Apply natural log. So once we apply natural log, this changes into x times natural log tangent to x. Please tell me if you all agree with this. We bring x in front as a power, and then natural log of tangent twice x. Is that okay? The next step is and you should say no, and I'll explain why. I'm going to apply limit as x approaches 0 from the right to both sides. So limit as x approaches 0 from the right from natural log y is the same with limit as x approaches 0 from the right of x natural log times natural log tangent twice x. And what you should say is this is not what you're asked to do. You're not asked to find the limit of natural log. You're asked to find the limit of y, not the limit of natural log of y. True. But I know it seems like a year ago or so, we said that as long as this function is continuous, is it? It's continuous on its domain. Yeah, it's continuous on its domain. We're allowed to do something. Right, swap the operators. I'm not there yet. I will find the limit of natural log y, whatever I get, and then I swap the operators and make a conclusion, and draw a conclusion. Ready? So forget about that idea for now. We're worried about this. So we're worried about natural log, x times natural log, and the limit. So this equals limit as x approaches 0 from the right. I'm going to copy it one more time. You don't have to write it one more time. I'm just going to copy it because I ran out of room, of course. Nobody's surprised about that. Okay, so when x approaches 0, this approaches 0. Slowly from the inside to the outside, where does this go? Good. Where does this go? Where does this go? Remember the graph of natural log. Where does it go? Here's the graph. Please remember the graph of natural log. I'm begging you, please, please, please. So when this approaches 0, of course 0 from the right, natural log approaches good. So now the limit is this. Is no longer 0 raised to 0. We're looking at a different indeterminate case. And you can say, so what? We haven't accomplished much. We have a lot. Changing the power into this, it's awesome. Because this can be changed into a ratio very easily. Look at the function and tell us, yes, Greg?
So it's not 0 times negative infinity?
Doesn't matter. The sign is not important.
Okay.
It is 0 times negative infinity, but it's not important.
Okay.
So look at this, and please tell me how we change this function in brackets into a wonderful ratio. With a very simple,
X over 10 to
I can't touch this. If I touch this, I will be in terrible trouble, because if I bring it to the denominator, it will have power -1, and when I differentiate, I bring down -1, I subtract 1 from the power, and it will never end. Exactly, like we did before. Please keep that in mind as a strategy. Try to work with very simple situations or expressions and bring them to the denominator, because this is a friendly function to differentiate the denominator. Bringing natural log to -1 to the denominator will be, because it's a function to a power. Okay, so now I check again. Let's check. The top goes to, yes, indeed. The denominator goes to, I'm sorry, infinity, negative infinity. Nothing changed. And the bottom goes to, careful, let's graph 1 over x. Yes, so here's the graph of 1 over x. So this is natural log x. This is the graph of 1 over x. 0 from the right. Where does this go? Good. The sign is not important. Are you happy? I can see it. in your eyes? You are. So this is limit as x approaches 0 from the right. It's exactly what we wanted. We wanted 0 over 0 or infinity over infinity. We got infinity over infinity, so that's awesome. So then, the denominator is the easy one. The numerator would be 1 over
Tangent to x.
tangent to x times
Secant squared.
secant squared to x times 2. Now we have to be very careful for several reasons. Number one, I don't like products in L'Hopital's room if I can avoid it. And I have a product or a ratio if you want at the top over there. So, second thing is, I would like to get rid of whatever I can, and I can. I can get rid of this. Where does this go? Yes. And this is times 2. I want to put the 2 in front. 2. Limit as x approaches 0 from the right. And if you want negative, because I want to take care of this too, and I flip the fractions and I get this. So I divide 1 over tangent twice x over this, and I flip and I get x squared over tangent to x. Yes, you will say it's 0 over 0, and I would have to agree. But I really would like to change this into sine over cosine, because cosine can disappear. It's a friendly function around 0. So this is negative 2. Limit as x approaches 0 from the right. Or we continue differentiating. But remember what happens. If I differentiate this, I get secant squared, which is fine. I can. It's just secant squared. That's fine. So it's 0 over 0. We can do that. So this is 2x over secant squared of 2x times 2. That's fine. I was thinking of secant, which is a product, so that's, I didn't want to go into that. But it's perfect. So the numerator is 2x. The denominator is secant squared of 2x times 2. I simplify the 2 with the 2. And now I can plug in 0 because this approaches 1 and the numerator approaches 0, and the answer is agreed. That's 0. This is not done. Now I copy the starting point and I copy the last point, the last answer. So the limit, I claim now that the limit as x approaches 0 from the right of natural log y is 0. After all this work, limit of the natural log is 0. Based on continuity, I'm allowed to swap the operators. So I have natural log of the limit as x approaches 0 from the right. If you remember in continuity, I mentioned this is a very important theorem, allowing us to swap the operators. We're going to use it a lot. And here's when. So now here's my question to you. Natural log of what is 0? There's only one number whose natural log is 0, and that's the answer to our limit.
1.
So, the limit as x approaches 0 from the right from tangent to x raised to x is 1. You didn't expect that. I will not believe you would say yes, but you did. Okay, so in summary, super long. I know I write big, but I still needed 3 pages to finish it, right? So what did we do before we choose another problem? First we had to test, and we got this. Then we named the function. Then we applied log to both sides. Then we applied the limit to both sides. Then we manipulated this as much as possible to get it into 0 over 0 or infinity over infinity. Then we used L'Hopital's rule, twice actually. Then we got the answer for the limit of the natural log. We copied the starting point and the end point. We swapped the operators, and then we thought, okay, natural log of what is 0? It turns out there is only one number, and that is 1. Therefore, indirectly, you could say something like this. Instead of this, we determine the limit of that power. I'm not friendly. It's a lot of work. So please choose if you'd like. Those problems are between 55 and 66.
I have a question.
Yes, please. Huh?
So once you get like 0 over 0 or infinity
Then you can apply L'Hopital's rule.
so you keep using that rule until you
As many times as you have 0 over 0 or infinity over infinity.
okay, you do it until you get
Till you get a number or infinity.
Okay.
Whatever you get. But you, as long as you have 0 over 0 or infinity over infinity, you can continue and continue and continue.
Okay.
If at some point in time you no longer have one or the other, you cannot apply L'Hopital's rule. Then you have to stop and regroup. Okay. I think we need another example like this. Are you okay with that? Or yes, of course. Would you like me to choose, or I can show you the book and you choose? So these are the problems from 55 to 66. $60? Okay. X raised to natural log 2 over 1 plus natural log x. I don't know if we'll allow him to choose again, but that's for now it's okay. We'll see what this comes out to be. Let's take a look. Okay. We said 60. Limit as x approaches infinity, I think it is. Yes, infinity. X raised to a fraction, natural log 2 over 1 plus natural log x. Actually, maybe something quite friendly. We'll see. I've never picked this. I encourage my students to. One of my colleagues was observing me in class, because we observe each other when we apply for promotion or if we tenure or something. So one of my colleagues at the end of the class said, "How do your students make problems? Are you crazy? What about the element of surprise?" And I said, "Yeah, what about the element of surprise? I surprise them with tests." I mean, what do you mean? What do you mean, what about the element? I thought it was funny. Okay, so that's the element of surprise, of course. Okay, good. So we have to plug it in, we have to test, we have no idea what this means. We start with the inner function. Where does this go when x approaches infinity? Remember the graph of natural log. This goes to good. 1 plus infinity is a number over infinity is good. So the numerator goes to 0. The power goes to 0. Where does this go? Yeah. So another ugly one. Of course, we expected that. So infinity raised to 0. Perfect. We take the function aside. Natural log 2 over 1 plus natural log x. What now? Now this should refresh our memory or bring back memories, if you want, on that logarithmic differentiation, correct? That's how we started with logarithmic differentiation. We took the function aside because we could not differentiate x raised to tangent. So we had to name the function, we had to apply log to both sides. So this is not a procedure that we have not seen before. Okay, next. What do? Natural log y equals natural log 2 over 1 plus natural log x multiplied by natural log x. Is this okay?
Yes.
We agree with these steps. How is this okay? Anyone? Questions? Good. So I have the function, I applied log to it. What is that x then? I apply what to both sides?
The limit.
Yes, the limit it is. So I apply the limit, and it was x approaches infinity of natural log y equals limit as x approaches infinity from natural log 2 natural log x over 1 plus natural log x. Is actually quite friendly. Quite nice. Don't worry about natural log 2 is a constant, you can go in front. Don't even look at it. It's like 3. You can put it in front. So now, where does this go? Good. Where does this go? Excellent. Very good. So the natural log 2 times limit, x approaches infinity. The top prime,
1/3.
the bottom prime.
1/3.
Excellent. Look at how nice this is. So the limit is natural log 2. Now we copy the starting point, which is this, and the end point, which is this. We understand all steps. It's quite a very, very nice example. I didn't expect this. Any questions? Yes,
How
Greg?
do we get 1 over x divided by 1 over x?
Very good. So since we got infinity over infinity, natural log is a constant. I took it outside. When I differentiate natural log, I get this. When I differentiate this, I get 1 over x.
Okay.
And they go away because it's 1. And then I copy the beginning, which is limit as x approaches infinity from natural log y equals natural log 2. At this point, I do this. So I have natural log in parentheses, the limit as x approaches infinity from y equals natural log 2. In this particular example, I didn't even need to think. Natural log of what is natural log 2? Exactly. There's nothing else. It must be 2. Only natural log 2 equals natural log 2. Right? So then limit as x approaches infinity from x raised to natural log 2 over 1 plus natural log 2 is is 2. I wasn't looking at the right expression. The limit of this is 2. It can be anything else. This was nice and very much easier than the previous one. Do you think we need a third example? I'll be more than happy to. Or Newton's method. I'll be more than happy to look at another example if you feel like it. So we encountered 0 raised to 0 and we encountered infinity raised to 0.
Yes.
We want to look at another? Very good. Let's choose.
Um, 66.
Okay. Everything is 308. Page 308, 66. And that is limit as x approaches infinity, 2x minus 3 over 2x plus 5 raised to 2x plus 1. Okay, so please walk me through. Where do we start? Inside, from the inner to the outer. Okay, where does that go when x approaches infinity? And imagine you apply L'Hopital's rule. It's 2 over 2. Okay, I don't think we see that. Not everyone sees that. So we have to determine this limit of this. So limit as x approaches infinity from 2x minus 3 over 2x plus 5 is infinity over infinity, which allows us to apply L'Hopital's rule. The top goes to, yes, because we differentiate, and the bottom goes to,
2.
so the answer is perfect. So where does this go then when x approaches infinity?
1.
1. Where does the power go when x approaches infinity? And look at that. We hit the third power. We looked at 0 raised to 0, we looked at infinity raised to 0, and now we're looking at 1 raised to infinity. Perfect. So then next step. So we denote this by y. 2x minus 3 over 2x plus 5 raised to 2x plus 1. So one more time, the first step was to identify the case, because I don't know what to do. Second step is, once I identify and it's a power, either 0 raised to 0, infinity raised to 0, or 1 raised to infinity, then I know I have to take that function out, name it y. What will I do next? Apply natural log. So natural log y equals 2x plus 1 times natural log of 2x minus 3 over 2x plus 5. Do we understand? Yes, please.
Isn't 1 raised to any power just 1?
Very good question. Except when it's 0. 0 raised to 0 is not 1.
I know, but since the inside was already determined to approach 1 as x approaches infinity.
Right, but you mean 0 raised to 0, right?
No,
You're talking about 1 raised to infinity?
yes.
No, can't be anything. It's one of the 7 indeterminate cases.
Okay.
Yeah. It may end up being 1 by accident. So it is possible, but not always. That's why we call it indeterminate case. Nobody knows. Good, very good. Next step. I have y, I have natural log y. Apply limit to both sides. Excellent. So limit as x approaches infinity from natural log y equals limit of all this. X approaches infinity, in parentheses 2x plus 1, natural log 2x minus 3 over 2x plus 5. Okay, piece by piece, let's see the case now. Again, I have to check which indeterminate case that this is. Where does this go? Yes, this one goes to infinity. We already know where this one is going, just the inside. Where does the inside go?
1.
Yes, the inside goes to 1, but where does natural log 1 go? 0. So now we changed 1 to infinity into a much friendlier situation. This is much better than 1 raised to infinity. A very simple algebraic manipulation will change that into either 0 over 0 or infinity over infinity. How? And no, don't touch natural log, please.
2x plus 1 divide.
Exactly. Is this okay? Is it clear why those two functions are identical? When top go?
0.
0. Where does the bottom go? The bottom, like as a fraction. The whole thing, the whole denominator. So the numerator goes to 0. Where does the denominator go? 0, of course. It was infinity times 0, so obviously once I bring that infinity to the denominator, it has to be 0 now. Perfect. Okay, we're in business. I would change, for the purpose of differentiation, I would change this piece to 2x plus 1 to negative 1. But that's me.
Oh, that actually works when it's 1 over something.
Yes. Or 3 over. It would be 3 times 2x plus 1 to negative 1. Or 10 over. But not variable.
It has to be.
Yes, any number, but not variable. Yes. Okay, so let's start with the top. When we differentiate the top, what do we get? 1 over this, 1 over this,
2x plus 5.
2x plus 5 over 2x minus 3. And now it's a mess, but I have no choice. So it's 1 over that, and now I have to differentiate this using the, and I have no choice, using the quotient rule. Top prime, 2 times the denominator, 2x plus 5, minus the numerator, 2x minus 3, times 2 over 2x plus 5 squared. Now the denominator, negative 1 times 2x plus 1 to negative 2 times 2. Is this okay? No, we're not there yet. I know. So the top line is 1 over, so that's why I already flipped it. And then numerator prime is 2 times the denominator minus the numerator times the denominator prime over the denominator squared. And now I differentiate this, negative 1, 2x plus 1 to negative 2 times the inner function prime. Okay, at least the log is gone. You should be happy. That was even worse, right? So negative 2 over 2x plus 1 squared. And now piece by piece, let's work on the numerator. So we have a 2x plus 5 over 2x minus 3 times. I want to pull a 2 in front from here. And then I have 2x plus 5 minus 2x plus 3 over 2x plus 5 squared. We're not far. Few more steps. Luckily, these two go away. Also, one of these with one of these. So then, limit x approaches infinity. Let's see what is left at the top. 5 plus 3 is 8 times 2. So 16 over this product. 2x minus 3 times 2x plus 5. And then I flip this into 2x plus 1 squared over negative 2. So I simplify the 2x with minus 2x. I had an 8 times 2, which was 16. I have 2 factors in the denominator, and then I flip the denominator. The 16 with negative 2 will give us a negative 8. And this is friendly. Because you can expand if you want. You don't have to. But it's better to expand. So 4x squared plus 4x plus 1. And the denominator is 4x squared minus 6 and plus 10 and minus 15. The reason why I expanded is because it's a rational function, same degree over same degree, leading coefficient over leading coefficient. You know where this limit is going. If you say no, I don't, then I will have to show L'Hopital's rule because this is infinity over infinity. And that's okay. If you say no, I don't see it, let's apply L'Hopital's rule. But I had to expand it. So the numerator was the first term squared plus 2 times the first times the second plus the second term squared. And here I have 4x squared, positive 10, but minus 6, and then negative 3 times 5. So do I need to show this limit, or we know where this is going? Do we agree? Do we see why it's going to 1? We're not convinced. That's fine. So let's look at that. So this is negative 8. You agree that it's infinity over infinity. So we will apply L'Hopital's rule. So 8x plus 4 over 8x plus 4. And they are the same. So this must be 1. So that's why the answer is negative 8. We have the last step, and 5 pages earlier, I had the beginning. So then natural log, so limit as x approaches infinity from natural log y is negative 8. Finally, I can swap. And then I'm going to ask you again. So the answer is no, it's not 1. So what can I have here so that when I apply natural log to it, I get negative 8? So remember, I need something that brings the power down in front of the log. And that answer is negative 8.
So e to the negative 8.
E to the negative 8. So then the limit, as x approaches infinity, from, I even forgot the function, 2x minus 3 over 2x plus 5 raised to 2x plus 1 is e to negative 8. And literally, yes, I know I write big, but still, 1, 2, 3.
That was easier than the second one.
Say it again.
That was easier than the second one.
Really? Okay, the last thing I would